Hello, in this video I'm going to say a little bit about Van de Graaff generators, and you may have come across these maybe in a science museum or a demo at college or school, because people love to demo these things. They do look quite impressive. If you've not seen one in action before, the bit that you're really looking at when it comes to the demo is that we've got these two spheres. We've got a large sphere, we've got a small sphere, and we're going to set up a very, very large potential difference between these two spheres, to the extent that we get electrical discharge. We get mini lightning sort of zapping across the gap between the two spheres. So it does look quite impressive because you've got this sparking going on as we're zapping across the gap. So how do we go about setting up this really high potential difference? I mean, we're talking here in the megavolts, millions of volts you can set up on small Van de Graaff generators, and much larger on the big Van de Graaff generators. So how are we actually doing this? Well, we're wanting to get accumulation of charge. So really that's meaning we're moving, more often than not, electrons away from the large sphere to leave it positively charged, and then onto the small sphere to make it negatively charged. Now, this is going to require energy input. We're going to have to do work to do this, because we're pushing more and more electrons onto something which is already negatively charged. So we need to put energy in order to overcome that repulsion, that electrostatic repulsion between the electrons. And that energy in, I mean, it might be, as you see on some old Van de Graaff generators, where you've got a handle where you're actually cranking the handle mechanically in order to put energy in, or in this case you'll see they've got a little electric motor down there to power the mechanism. And the mechanism that's driving all of this is sitting inside this insulated column that the large sphere is sat on. Now, we want this column to be insulated first of all, so we're controlling the flow of the electric charge. We don't want to, if we just create something which is strongly positively charged here, then without it sitting on an insulator, we're going to start pulling in electrons from, say, this metal base down here or other locations. So we want to isolate this large sphere as much as possible. So that's one reason that we've got this insulating column. But then inside the insulating column, we've got this belt. So we've got two cylinders, one at the top, one at the bottom, which has got a belt going around it, like a conveyor belt. And this belt is being driven round and round these cylinders, either by, like I say, a handle or by an electric motor. The belt might be made of, say, rubber, maybe it's made of silk, something like that. The cylinders are made of some kind of acrylic glass, usually. So we've got these two different substances. They're rubbing against each other. So we're making use of what's known as the triboelectric effect, something which you've probably made use of, even if you don't know the name. So this is like when you slide around on the carpet in your shoes and then go and zap someone. That is setting yourself up as a mini Van de Graaff generator, really. So you've got the rubbery sole on your shoe, you're sliding around on some kind of acrylic carpet, and you're transferring electrons from the carpet onto your shoes. You're creating a potential difference. Essentially, you're charging yourself up so you can go over to someone and then zap them with your finger. Well, Van de Graaff generators are like that on steroids. You're cranking up the voltage to a much higher level. But the effect, the process is the same. We've got this triboelectric effect, this sort of rubbing effect, which is transferring electrons from one place to another. Now, this is going to be moving electrons from the sphere at the top down and out some cable and then off to the sphere on the right. So let's look at the top part of this just to get an idea of what's going on. So you get this comb, it's like a metal toothbrush, which is on the inside of the big sphere. So the big sphere is just isolated on top of this insulated column, and sticking inside, attached, is this metal like toothbrush, and that's pointing down towards the top cylinder. Now this top cylinder is getting positively charged, and the inside of the rubber belt is getting negatively charged because they're rubbing against each other. The between the comb and this cylinder, you're getting a strong electric field, which is actually ionizing the air between the comb and the cylinder. So we're pulling electrons from the air onto the cylinder. And we've now got this positively charged ionized air, which is then pulling electrons from the metal comb. So we're getting a transfer of electrons away from the large sphere and that metal comb onto the cylinder, then onto the belt, and then so on and so forth all the way through, and we can, you know, push them up to the small sphere. This is leaving the large sphere positively charged. Now, according to Gauss's law, so this is all part of Maxwell's equations. Now, we got Gauss's law, which describes how charge is distributed across surfaces. Now, if you've got a hollow conductor like this sphere is, so we've just got a metal sphere, hollow on the inside. Now, Gauss tells us a couple of things about this. It tells us that the charge is distributed evenly around the outside surface. So we've got evenly distributed positive charge because there is no electric field inside the hollow sphere. So, okay, we've got an electric field between the comb and the cylinder, but in general, inside the sphere as a whole, we have no electric field. So this is allowing us to build up more and more and more positive charge on the sphere in a way that we wouldn't be able to do from the outside. You know, on the inside, the field pretty much disappears except for where all the action is going on between the metal comb and the cylinder. So this is allowing us to get a massive build up of positive charge, move loads and loads of electrons off, and get this huge potential difference. So, like I say, Gauss's law is the description behind all of this. As I said in the video on Maxwell's equations, that's getting us into undergraduate level physics. So we're not going through Gauss's law in detail. You know, you can go off to other videos if you want to start getting into the details of Maxwell's equations. But that is the description behind the physics of all of this. So that is the process of how we're getting that huge potential difference. And then when we start getting up to, 5 megavolts or something, we get our little zaps. We get our discharge going from one sphere to the other. Like I say, you can charge them the other way around if you've used different materials for the belt and the cylinders, and then you could have a negatively charged large sphere and a positively charged small sphere. A word on why it's a Van de Graaff generator then. Well, the breakthrough in this accumulation of charge, because that was what we're trying to achieve in here. This was made by Robert Van de Graaff at Princeton University. So Princeton, well, that's New Jersey, I believe, if I remembered that right, in the US. And Robert Van de Graaff, he was working at Princeton in the 1920s and 1930s. And he made an improvement on existing methods for accumulating charge. So Lord Kelvin, who I've done a video on in the thermodynamics section, he had come up with an initial idea for accumulating charge by dripping charged water into a bucket. So you're building up charge in the water in the bucket, and you can get more and more charge in because you're using the GPE essentially to do the work to overcome the electrostatic repulsion. So you're using the work done by gravity in order to accumulate the charge. But it was Van de Graaff who came up with this idea of using a ribbon. And I think he started with a silk ribbon as this charging belt in order to drive this process. And there was more interest in this in the 1920s, the 1930s, because there was a strong motivation to set up a particle accelerator. If you've got very large potential differences, as we know, you can get very large accelerations of charged particles. So this seemed like a great way of constructing a particle accelerator. So we have different ways of going about it now. You go to CERN, then you're using magnetic fields and things like that. But back in the 1930s, when people were getting really interested in particle physics, then this seemed great. And in fact, it was Westinghouse Electric, one of the titans of electricity in the US back in the 1930s. I mean, they started crumbling in the 1970s and 80s and ended up getting taken over multiple times. Can't remember, they changed hands all over the place, don't really exist anymore. But yeah, Westinghouse Electric, they built what they called the atom smasher in 1937, which was a particle accelerator built around this principle. So it had definite scientific applications experimentally in that period between the wars when people were really getting into particle physics. And as I say, it was Robert J. van der Graaf who was the mastermind behind the big step forward in building up these huge potential differences. So there you go. I mean, they're interesting things. And the next time you see a Van de Graaff generator in the Science Museum or something like that, you'll know how they work.